Let's pick this apart, this equation, and look at each of the pieces individually. So I'm going to call this the left-hand side, this is the first term on the right-hand side, this is the second term on the right-hand side. So let's look at the left-hand side first. We have partial squared, partial x, partial y of gamma. So what does that mean? Well, gamma can be expressed as a function of shear stress, and eventually the e's are going to cancel here, so I'm going to drop that. So the left-hand side is 2 times 1 plus nu, and the second derivative of tau xy. Remember, we have a second derivative of x and y over here. Now let's look at the first term on the right-hand side. We have partial squared with respect to y twice of epsilon x, this is the green bubble, and through the generalized Hooke's law that we looked at on page 1, that's why I made it a green bubble here, we have the generalized Hooke's law with the Poisson effect on the sigma y, and again the e's are going to cancel here. And then the second term, partial squared partial x squared of the red bubble, which is epsilon y, and that is our generalized Hooke's law here. So the Poisson effect is on sigma x here. And again, the e's cancel. So the left-hand side is the 2 times 1 plus nu. The right-hand side, the first term. Right-hand side, the second term. And I'm going to put horizontal green lines under this. And this is a very handy-dandy little equation here. Now, let's say that we have no z variation here, so we're going to begin with equation 2.4-2, which are a green box. We use the green box around those equations. Those are equilibrium equations. So they are the equilibrium equations. They're not the compatibility equations, they're the equilibrium equations. And remember, they're in this kind of unusual format that are using derivatives of stresses. And these guys, what were they called? Body forces. So sometimes we ignore them. Typically we know whether to include them or not. So the equilibrium equations use derivatives of stress, which we've talked about a lot in chapter 2. The compatibility equation now also has stress in it. So I went through the generalized Hooke's law and I converted those strains to stresses. But notice the little subtle difference in here. This compatibility equation has a second derivative. The partial derivatives are second derivatives. And in the equilibrium equation, the partial derivatives are first derivatives. So what do we do here? We're going to take this equation and we're going to differentiate it first with respect to x and then with respect to y. We're going to take this equation and we're going to differentiate the first one with respect to x and the second one with respect to y, and then it's going to look like this equation. So we're trying to make it look like this equation. So take this one, this first equation, and differentiate it with respect to x. So I'm going to have a second derivative with respect to x of sigma x, and then I'm going to have a derivative of x and y on tau, and a derivative of the body force, and a 0 on the right hand side. Second equation, I'm going to differentiate it with respect to y. So I have tau xy with partial y partial x, and then I have sigma y with 2 partials, and then I have the rate of change of the body force. And you'll notice these two look very, very similar to each other, and the question becomes, does it matter which way, what order you differentiate it? And the answer, of course, is no. So let's just call these the same.